right. So yeah, so this is like I said, just going over the key highlights from chapter 3, storage and retrieval chapter. So this is how I saw it. I looked at this chapter in 3 main sections. One is, as this post here says, looking at the data structures that were talked about, that kind of underlie the database storage and retrieval uh, mechanism. The other part was transactional processing or analytics. And the third, which is not here, but third one, interesting one to me, was in-memory versus disk-based databases. So these were the 3 main classes that I kind of looked at in this chapter. And if we talk about the data structures first, right? Uh, instead of, I mean, so let's kind of talk about first log structured versus B trees, right? And feel free to chime in at any time. So the way I think about this is log structured is something that allows me, or I can use log structure when I need to support an append only, data structure, right? And the benefit that I get from that feature is that the write throughput would be pretty good because I'm just appending at the end. So it's kind of sequential for me, right? Now coming to B trees, like I'm trying to do a parallel, like, one by one comparison. So if I think about B trees in the same vein, they are in place, they are mutable data structures, right? So you are not appending to them. If there is a data value present and you want to update it, you're not going to add another one, another copy of it, but you're going to overwrite it. And the benefit of that would be, if we think about log structured, since we are keep appending the values, right? The same key, there can be multiple values for the same key. And if I have to read the value for a certain key, I would have to, look through the multiple segments or, multiple values of that key and pick the latest one. But in B trees, there is only one value that's present. So that makes it, easier. So I'm thinking of, as I'm talking about it, I am in my mind, I have structured it in a way that for every feature of the data structure, what does it offer to me, right? So this feature of append only versus in place update, this is how I interpret it. That if I were to design a data structure for write throughput, log structure has a benefit. So that's point number one. The other way I looked at this is, it's kind of spread out here, but the other way I looked at this is in log structured, so log structure breaks database into variable size segments, whereas B tree follows the fixed size blocks or pages. And in B tree, you always read or write one page at a time, right? Now, what happens when you have a fixed size data structure, right? Like fixed size page. The problem there can be that it can lead to fragmentation, right? If you have a page. Was there a question or?
Yeah, I was just saying wastage of memory will be there in that case.
Yeah, correct. Wastage of storage and, memory if you're storing it in memory. Yeah, right. So there would be overhead there, which is not the case with log structured. The other point I noted there was in log structured, based on the way they store data, there is this compaction process that runs in, right? Which has its benefits, but also it can interfere sometimes with read or write, ongoing read or write performance. And also the second part is that, let's say you start with the log structure database and your disk is, there's no data on the disk. Now, when you start writing, you have the full bandwidth available, disk bandwidth. But now as the data starts growing, you also have compaction kicks in, and the disk write bandwidth will also be split, right? It needs to be shared between compaction and the actual writes. So that was another implication of the way they store data. These were my points about these two data structures, or when I would use one over the other. Is there anything else that anyone would like to add, or any questions around this?
So in case of fixed size, let's say we are using some part of the memory and some part is left. Okay.
Yeah.
Yeah. So let's say if such parts are left in every fixed block, so can we use them? I mean, let's say we get a database of size such that if we aggregate all those remaining parts, and if that same can fit into that, can we use something like?
Yeah, so that is, I mean, that's a good point, right? If, as long as there is some like there are algorithms, right, where you can kind of, bring the data closer or reorganize it. But I believe it depends on, I mean, if it's a fixed size block, I'm not sure, because you're storing in B tree, you're storing like you have a page, and let's say every record in your database, in your table is, let's say, I don't know, 8 bytes, right? So it's like
Okay.
kind of fixed there. Now, if because of some, like a multiple, let's say the page is 8K page, and you are left with few bytes in that page, right? Now, because the record size is, 8 bytes, and if it can't use that space, then directly it may not be possible, but if there are, I'm sure.
No, then in that case, the bigger record we can chunk and then put remaining in each of the fixed block. I'm not sure, like just
No, I don't think you can break the record, because it's like that key value thing, right? That's where the idea of fixed size things come in. So if a record can't fit in a certain page within a given space, then you move on to the next page.
next block.
Yeah, yeah. So
And two records can be fit inside one fixed block. Like let's say if it is of 8 byte size and we have a record of 4 byte, 4 byte. So
yeah,
both of
yeah,
them we can.
yeah, yeah. On the same page, yeah,
Yeah, makes sense. Thanks.
yeah. Um, Anything else on this?
Hey, just one thing I want to add here is that if we are looking for range queries,
Yeah,
then SS tables like and B trees are more efficient because they have like they have kept data in a sorted way rather than hash index.
correct, correct. Yeah, I was going to come to hash index and bring that point,
Yeah.
but yeah, you're right. So
You don't need to keep the data. You can also have the pointer. You have on the B tree. You can have a pointer
yeah,
to the data.
correct.
So if you have a pointer to the data, then it's unlimited. You can have any data at any size.
Oh, you're talking about the storage. Okay. So you were talking about the fragmentation aspect?
No, I'm talking about a B tree. That I would. You can start the data, in a block in the B tree,
Right.
or you can store, the pointer to the data there.
Sure. Yeah.
So if you start it on the leaf of the B tree, that limit, right? But there's a limit number of a byte storage you can store there. But let's say you have a video or an image or something big, you can save it somewhere and save the pointer, at the
So my
B
point
tree.
was, yeah, you're right about the pointer stuff. Though I think just to clarify, what I was trying to say was, like, for a node, right? A node has a key value. So depending on the size of that, right, that is an atomic thing that you can't split. But yes, of course, it works on the pointer and
The node is like if it's an intermediate node, you don't store data there. You store data at the leaf, of the B tree.
right. Okay, so we are good on that. And now just touching on this hash index. that Abhishek was pointing to. So just the way it says, right, hash index. So you have this data structure which can help you speed up the reads in your database. So rather than hitting the database and searching through it, you can have a hashing mechanism where you try to find the hash key, and then you find the offset in the actual database. So that's true. And there were two interesting points we talked about when we were going through the chapter on this. One was this range query point that Abhishek pointed to, that hash indexes are good for exact lookups. But if you were to support range queries, then they are not the best way. Then B trees or SSTables are better, because hashes are like, hash keys are not put next to each other, right? As it just says, it's like a hash function, whatever hash key that gives, it can be randomly, split, and there's no connections or links between the different keys. So hashes are good for exact lookups, not the range queries. That's one. And the other point we had a quick discussion about was this memory constraint, right? You keep hash tables in memory, but then there is a limit because of the memory constraint, how much your hash table can grow. So what are the solutions there? And one solution is how you can make your hash table small by ensuring that you don't keep key value pairs for every entry in the database. You make it a sparse index. And I'll show an example quickly. The other idea is that, so the other question was, I mean, that is considered a good solution to how do you make your hash table small. But the other question, parallel question during our discussions came up was, what is the challenge if you keep it on disk? It's not like that you cannot keep it on disk, but the challenge is that because of hashing, the hash keys are just spread out everywhere, right? And that incurs a bottle like a hit on disk-based systems, right? When you have to switch from one page to another, that's a performance hit. Whereas in memory, it's all like the pointers, so it's not a problem there. That was some of the key points on hash indexes. Now, before we move on to this transactional processing, I also, since we are talking about the summary, I also wanted to share this part here. Can you all see the slide deck?
Yes.
Okay. So this is something I just created initially, but I felt that, everyone is pretty on board with everything, so I didn't post it. But since we are discussing the summary, I think I can just quickly go over it. Why is it not? Oh. Okay. So what I thought the major takeaways, right? If I were to pick the major takeaways from this chapter and how do I map it to some learnings that I can take with me on either interviews or, general like key takeaways here. So this is what I gathered, that this chapter kind of tells us about in-memory versus disk-based and mutable, immutable. This is where the SSTables versus B trees comes in, mutable versus immutable. Then the question, we often run into system design about you have a database and the question is it read right? Is it read heavy or write heavy? So this question is also kind of addressed in this chapter. Then what type of queries that we just talked about, exact lookups or range based. And then the last point is about the transactional processing versus analytical that we'll take up shortly. So when I started this slide deck, I looked at it as a scenario-based, kind of workflow that if I'm given this scenario, right, I have to design a disk-based system that can support read and writes, right? So the simplest approach is what is, this is the example shown in the book. So you just do append-only storage. The good thing is it's simpler to write, but the reads will take a hit because you have to scan the end of the file to read the latest record, right? And also there is a space overhead because you will store, if same key has multiple values, you're not going to delete anything, but you're going to keep appending. So that's first. So now that leads to the question, from here we can ask ourselves that if it's an append-only storage, then how are you going to manage the file growth, right? It's going to keep increasing. And one of the solutions there is you can maintain the most recent value for a key. You don't need to store all the values, right? And this is where the idea of compaction comes in, right? So here is an example. I mean, I just pulled all these screenshots from the book. So most of the stuff you would just know. I'm just skimming through it. Let me know if anything is not clear here.
On the previous slide, can you elaborate more on the in-memory versus disk?
Which one?
The previous one. Go back one more slide if you could.
Oh, this one.
Yeah. The first point right here.
Yeah. So if we want to jump there, the idea is, I think this is something we touched upon in the last session. The point here is in memory versus disk-based, right? So what is, before even distinguishing, like what's the benefit of one versus other, or let's go that route. So what happens in the two cases and what are the implications, right? So what happens in databases is when you have a read request, right? And I'll explain the situation for both of them. So when a read request comes in, if your database is in memory, right? The way OS looks at this is that it knows that all the data in your database is present in memory, and there is also a copy which is on disk for durability. But the operating system, the key takeaway in this sentence is that operating system knows that all the data is present in memory. I don't need to hit database for reads. So when a request comes in, like a read request, it will just, directly look into the memory. That is point number one. Now, what happens in the same situation in a disk-based system, right? Disk-based database. When a read request comes in, where do you think the data can be? Can it be in memory or disk or either of them? Where do you think, where are the possibilities for the data?
It could be in memory if we already, we cache it,
Right.
or
Exactly,
somebody
right?
already.
Right. So if you have already read that data, that may be present in memory, or if it's not in the hot, data, it may be on disk. So it can be on either locations. So there is this concept of page table that comes in. That's an additional data structure that is maintained. So when a read request comes in, there is an additional, translation, like not translation, but first of all, it's using page table. It checks if that data is in memory. If it's not, then it goes back to, there is additional data structures like translation, lookup buffer, and all those. So there are additional data structures that are required for a disk-based database, right? Because data can be anywhere. Whereas in memory, it's faster because you directly hit the memory. That's number one. The other thing that I think you guys did discuss in the last session was how, if you think about like the B trees, right, on the disk, how they are, we talked about this node key and how the nodes are connected. So in our mind, when we have a node and it's connected to another node, in our logically speaking, we can see, okay, this is connected to that. But when in actual storage, they may not be placed next to each other, right? So they may not be on the same page. So what happens in disk-based systems is the way the data is stored, it can require a lot of, maybe scanning multiple pages and going through like one page to second page, and second to third, and third back to one. So because of this link structure, there are a lot of jumps in, and that takes a performance hit, right? Whereas in memory, it's all in memory. There is just pointers navigation, so it's much faster. So yeah, that was
Okay. Yeah.
my understanding. Yeah. So yeah, so this is where we were. So we were saying like how to. So I kind of, I decided I had another pen and paper diagram where I went through this whole discussion as, okay, I start from this scenario. What are the challenges here? So I branch it out and then I think around those. So this is how I have presented this slide deck. Hope it makes sense. If any confusions, let me know. So yeah, here I discuss how do I handle the file growth. So answer is compaction. But then the next question that comes is that with compaction, it can also interfere with my ongoing writes, right? So how do I handle that? And then here in this diagram, it is only showing one data segment, whereas the same key value or the same key can be present in another data segment as well. So how do I handle that? And that is where, so I took the first question. So how do I ensure that reads and writes are not blocked while compaction is launched? You cannot avoid it completely, but the idea is that you run it in a background thread, right? And you break the file into segments and you run compaction in a background thread. And this is one point that Leon helped me with. I wasn't sure about this one, but thanks for pointing this out. So the question was, can writes be impacted by compaction too, right? Read or writes. So if you think about the disk bandwidth, this is one of the points I touched before. So if you talk about disk bandwidth, it is finite. So compaction and the writes will share it, right? So there will be impact on writes. So now the other question that we talked about on scenario 2 was, rather than doing compaction on just one segment, right? The same key can be present in multiple segments. So that's where the concept of merging comes in. So you are not only compacting key value pairs in one segment, but you're also merging it with the records from other segment. So that's where the idea of compaction and merging comes in, and it helps to reduce fragmentation, right? Pretty straightforward there. All right.
Hey, Dippy, one question here. Also, can you please explain, how does it interfere with the rights?
Yeah, so the thing is, if you look at this compaction process, right, what it's doing, it's trying to, when this compaction runs, it allocates a new segment, right, where the data compacted records will be written.
Right.
And it goes through this segments and it's actually writing, data to the new segment, right? So there is a write operation going on internally, right? Versus this is internal writes going on to optimize your storage, whereas there are end user, facing writes which are coming to your system.
Yeah. So in this case, okay, I'll let you complete first. Yeah.
Yeah. So I mean that is like two different types of writes going on. So that's where the write bandwidth would be.
Okay. So I would like to add to this. I'll explain in terms of what is happening in Kafka. So that's why this question.
Okay.
So what happens in Kafka is we have what is the log size? Okay. What is this? What is the size you want to maintain for this topic? Okay.
Yeah.
So if you say 1 gigs, 900 MB, just 3 chunks of segments. So what it will do is it will keep 3 segments ready. Okay. So initially it will start writing to the first segment. When the first segment is full of 300 MB, it will move to the next segment. Okay. When it moves to the next segment, which is segment 2, it will run a compaction on segment 1. Okay. So it will make sure that after segment 2 is complete, okay, it will move now it is doing a compaction of segment 1 and segment 2. Writes are not affected. So that is the reason I asked this question, how are writes affected? Because writes are always happening on the latest segment, not on the previous old segments.
Sure, that is true. So what about the situation? So you're right, like it's not that it's hitting the same segment for the user rights and compaction, but what about this new segment that's written, right? So on my disk.
So, right. So it creates a new segment. This is what I feel. It creates a new segment, and internally there is a background thread. It also depends on how many threads you want to set for compaction process.
Correct.
So that thread will create a new segment altogether and delete the if it is processed all of them, it will delete these two segments and create a new segment.
Correct. But won't it still, like, that's where the write bandwidth is coming in, right? It's doing some work to write data to this new segment, right? And this is happening by some thread in the background. And then now there is another thread which is consuming the user rights request, and it's writing to a whole together new segment, right? Which is not interfering with this one. I agree with that. But my question is that since there are two parallel, so to speak, writes going on, right? Even though if they are in different segments, but there is write bandwidth that is used for the disk.
Okay,
So,
we can take this offline, or maybe.
So Prashant, like to simply say, so your hard disk,
text, yeah.
It will support, let's say, 5 writes per second, right? Like there is a limit in your hard disk. You cannot give 5,000 writes per second. So let's say that limit is, for example, 5 writes per second, and it does not matter what thread who is doing, but there is limit of 5 writes per second. Now, if you have a background process which is already consuming 3 writes per second of your disk, 3 writes per second bandwidth, then you are only left with 2 writes per second of bandwidth.
Yeah.
Right? So they are not interfering
so yeah,
with
in
each
that
other.
case, yeah.
Yeah, but they are just
they're using that bandwidth.
Yeah.
Then
okay.
Another thing is in Kafka, I think Kafka it define a segment different than the segment being defined in this book. A segment defined in this book is we don't need to compact it because in a single segment that already compact, everything is unique in a single segment.
No, it
right?
Right?
Because think about a segment, as write to the disk. The segment from a let's say a in-memory tree, in-memory let's say supposed to be binary search tree, and then at one point that tree is right into a file segment. Then in a single segment, there's no compaction. It's all unique. The only compaction in this case is it have to be more than one segment, so we can compact them, put remove duplicate and put them into a single segment. Does it make sense?
Yeah, so you're
because you think about it, how they generate a segment file, where that segment file come from. It's from a tree, an in-memory tree, right? And periodically, it write to the segment, or when the tree bigger than certain size, it write to a single segment.
Yeah, I think we are all on the same page about how, what segment.
No, but the previous speaker, he say like, there's 3 segment in Kafka, right? And then once it done with segment 1, and then it move to segment 2, and at that time it begin to compact, segment 1.
Yeah. So I think you were just trying to give a general example discussing the disk write bandwidth issue, like about when I was making a point that, one segment is compacted and how that impacts the write bandwidth. But I don't think it was,
Did he say that there's 3?
Yeah.
Yeah, then need to clarify that. Yeah.
That the context was.
Hey, Leon, I did not understand your question.
No, my question is, you know, within a single file segment that
Mhm.
are unique, that are the key value. I mean, all the key are unique, right? We don't. This already compact. Within a single
Mhm.
file
Okay.
segment. This already compact because
Right.
all the key is unique already. We only compact, you know, if we have more than one
More than
file
one
segment, then we compact, we put
Okay.
them.
Yeah.
Yeah.
Yeah, sure. I mean, I think you're talking about the Kafka example that's what.
No, but yeah, I'm not getting it. Like, yeah, we compacted and we kept it in one segment. What next? I mean, what is your question?
No,
I'm
I
still trying
think
to get to the
Leon
question.
is trying to highlight the fact that, correct me if I'm wrong, Leon, but I think he's trying to say that in this diagram, the way I'm showing it for log structure, right? Even
Mhm.
one single segment is having, let's say, multiple values for the same key, right? And I'm compacting it. But what Leon is saying is,
Right.
in Kafka, when you have a single segment, all your key value pairs are unique. Like there is no.
No, I mean in this one, I thought, maybe I'm wrong. No.
Yeah, this is
No,
like.
see, so
But I thought
if your system is not doing anything, not doing any writes, then it makes sense that okay, you have a set.
I don't see
If there
how.
is some key, you know,
No, so there can be in general based on, I don't know about Kafka, but in general, when you go back to the book, even within a single segment, there can be multiple values like you see here, this mu, right?
How it could be, because remember we use the tree, right?
No, it's not about the tree, it's about the append only storage, right?
No, we append
I
on,
would
but
say
we create the tree
so
first. We create in-memory tree first, remember, and then periodically we write data from that tree to the file.
Right. So you're talking, so I am starting from you're talking about something like here, that you have an in-memory tree and you're writing a file, but I am actually at an early use case. I think given that
yeah.
we covered the chapter, we all know a lot more than what this picture is showing. So that's where we are jumping a little.
Yeah, I think we're discussing a problem which is, you know, yet to come in the next scenarios.
Yeah, yeah,
Okay.
yeah, right. Correct. So, okay, so let me quickly run through it because we have what, like 5-10 minutes. So yeah, I was at the point, so we use this hash structure to optimize the reads, right? We can store the offsets and stuff. And then I talked about, how can we maintain it in memory? So that's where the idea of sparse index comes in. So we don't maintain key value pair for every entry, but it's for the every segment, right? So that will reduce the number of key value pairs. And I think, Leon, that kind of touches on what you were pointing to, that, you may not have like a unique duplicates within a segment. And here we also talked about how you can optimize this search criteria based on Bloom filters. So because it's a sparse index, so if I were to look for the key, let's say, something that's not present in this, my sorted table, then if I don't use Bloom filters, I would have to find the closest one in the sparse index and then navigate that segment. And then eventually come up with an answer that it's not present. To optimize that, we can use this concept of Bloom filter, which tells you, which is good for detecting true negatives. I'm kind of rushing through a bit because we really want to close on this, and I think we all are pretty, good with the concepts here. Then there is this concept about if how we can minimize for any data that's present in hashmap. That's if a memory issue occurs, how can we try to minimize the loss there? And one of the answers is you can keep taking a snapshot of hashmap and store it on disk from time to time. And the second idea was that this write ahead log, right? That is very a common paradigm in databases. that to maintain durability, you use this idea of write-ahead log. So even though you don't persist your data in data files, but you make sure that all your modifications are recorded in write-ahead log before user gets a commit message.
Hey, just to add to that, so we added to the write ahead log in terms of recoverability as well, not just terms of durability.
Yeah.
So if there is any failure, we try to recover from that write ahead log.
Yeah. Okay, so this is the point. This is where I kind of make a basis for why hash indexes are not good for range queries, right? You would have to, you're given two data values. You try to find the segment with the first one and then the second one, and then try to read through from first to second. But a better approach would be use a tree data structure, as we talked about. So we can have sibling pointers to maintain, to answer range queries. So this is kind of going from a problem, which is like why hash indexes are not good for ranges, and then moving on to a solution which says trees are good there.
But you kept the data sorted, right? So wouldn't the range queries be easier still? Because you can, you know, the nearby location where the data is.
In where?
So you said that your data is sorted segment file, right?
Right.
So that means your data is sorted.
Yes.
So then the range queries should not be a much of an issue.
Yes, it would not.
You said
No, but the thing is, let's say I have two values, right? So you are right that because it's sorted, so I can just scan through it. But now I don't know where my second, page, if it's not directly present in this key value, first I have to locate the segment where it's present, and if it is present, right? Like for example, if I say give me all values between 1 and 5, right? And let's say 5 is not directly present here, right? So first I would have to find the segment. First I have to figure out if 5 is present. I'm trying to think through.
yeah. So that's why you have the sparse index, right? Which will tell you that if
No,
one.
yeah, but sparse index will give me a hit if the value is not present. Let's say 5 is not present, and let's say this value is, let's say 4, right, or something.
But then you look for 7, right? You look for the next one. Let's think about the range within the binary tree.
Correct. So you look for the next one, but then you search through that whole thing. Let's say that value is not present, right? Or even if I use Bloom filter for this. Okay.
So the problem of range queries was when we were not keeping sorted, like the very first data structure append only logs. But these sorted and B trees solve that problem.
Oh, okay. Then I got confused here. Yeah. Okay.
You will have multiple segments, right? I mean, so it will just give you a range of what the data is in that particular segment. It will not tell you whether, so you might happen that you might have to read every segment. That range might have overlapped with every segment, and you might have to read every segment file, right?
Yeah, but it does support the range query. You might need to read from multiple segment file.
Yeah.
No, okay, yeah, that's a good point today. Yeah, that if your values are in different segments, then again you are taking
Yeah, that's what I was pointing to. Yeah, I was getting confused though, but I was thinking of the values are in different segment, that it's not a simple scan then.
Makes sense. Yeah.
Yeah. Okay, so this is, I think this is, I'm just talking about how SSTable is maintained. You can skip that. But yeah, this is where the slide deck ends. So kind of key takeaways: read write latencies, space overheads, keeping data in sorted manner. Now let me quickly, in 2-3 minutes, just jump to this concept about transaction processing and OLAP. Can you guys see this notes page, like transaction processing that I'm highlighting?
Yeah.
Okay, so the idea of in general, rather than going into some text here, the key takeaway here is transaction processing is more like, it's also called OLTP. So it's more like the, let's say a banking transaction, or, you take a retail store at a checkout counter, that's a transaction processing, right? You're kind of, so that's an example for user. But from the database standpoint, the idea is that you're trying to process a small bunch of records, like a row at a time. For example, if you're updating, um, some record, like let's say, user deposit or user's balance. So you're updating that. So there is only one row that's hit, or there may be a small number of rows. But in case of analytical processing, it's more for like drawing analytics, statistics, right? Or reporting. So you're reading all these, records, like thousands and millions of records, and you're kind of summarizing them. That's an example of analytics. So from that standpoint, I would say that's where the idea of column storage comes in. So what happens in column storage is you have, let's say, a database which you're maintaining as a row-based store, and it has 10 columns, right, in a row. And one of the columns is, let's say, salary, right? Now, if you maintain a row-based database and you're given a query, you issue a query saying, give me the average salary of employees, right? Then what you're doing is you're reading all the rows, all the 10 columns in every row, and you're just, pulling out or, processing the salary column. Now, what's the problem there? The problem there is that this is the biggest thing in databases, and especially this comes in disk-based databases, that the biggest performance hit that you get is about the number of pages that you have to bring in from the disk. So anytime you want to optimize the database operation, this is the trend you want to focus on. You want to minimize the number of pages you read from the disk. So from that perspective, you can think that if I'm storing my data row-based, then page is 8K, right? And my row size is, let's say, as an example, 8 bytes, right? So I'm storing 8 bytes, then next 8 bytes, and so on. Whereas my query is such that I only need to read 1 byte from every row, right? Which is salary column. So that's not good, and that's where the idea of column store comes in. So rather than storing your data in a row-based fashion, you store all the values of a single column together, right? So you store all the values of salary together next to each other. So you can now think that if a query comes in, which requires average salary, imagine how much you are saving in terms of reading data from the disk. You're only reading that much salary column. And the other benefit is the compression. So if you're storing the same kind of data together, you can run all these compression algorithms like run length encoding, and there's so many out there based on the data type. So you can run compression on them, and you can save not just the storage, but you can also save the bandwidth, like the network bandwidth, that when you read data, you're reading compressed data and so on. So this is where the idea of column-oriented storage comes from. Let's see. I think that was.
I have a question about the row.
Yeah.
Not like on the normal DBMS, right? They save the data in the row. Let's say, a row have like 20 column, right?
Yeah.
And I'm interested in only one column, but then when the process, they still need data from the whole row into memory, and then only, maybe parse the data and give me only one column,
Yeah.
right?
Yeah.
It does not know how to go directly to this and read that column alone. I have to read the whole row in the memory.
Whole row at a time, yes.
Yeah. That's why it's costly. I see.
Yeah,
Okay.
yeah. It's kind of wastage, right? Like you only need certain chunk of data, and you're reading all this extra data. Yeah.
So, DP, can you again explain this column?
Yeah, sure.
Thing?
So
Yeah,
let me quickly pull the diagram. Actually, that will be easier.
sure. Thank you.
Was there any cutting edge databases which
Oh,
currently
we use,
support columnar
yeah.
way of
So like,
storage?
yeah. So I can speak from my experience. I'm sure there are a lot many, but we use this column-oriented storage day in, day out. Like I work with Microsoft SQL Server, and we work on like terabytes and of data, and column storage is what we use like by default for analytical queries. Not the transactional, but analytical. Um, so Microsoft SQL Server heavily uses it. I mean, in Google itself.
SQL. And there is also the SQL data warehouse, right? Which is
Yeah. All flavors of, like when you say data warehouse, right? That itself like lends itself to column.
Oh, right. Okay.
Because it's analytical, right?
Yeah.
So yeah, so this is like an example. Can you see the web page I brought up?
Yeah, I can see it.
Okay, so here's an example, right? On the left is your table, right? If you store it in a row-oriented manner, then this is how you're storing like full row, right? And after that, you store the next row, right? And so on. Whereas in column-oriented, and now when you have to read, let's say one column, you will read this whole thing, then this thing, and then pull out this column, right? Whereas in column-oriented storage, you can, I'm not sure, yeah, this is a good example. So in column-oriented storage, you store the first like column, 1, 2, 3, first together, right? And then you store the second values together and so on. So now if I have a query which only deals with, let's say, this column, right? Then I can just pull this block. So you can think of this rectangle here. This is like a block in, or a memory or a disk page, right? So the question is, what is the most meaningful information that you can pack in a page based on your query pattern, right? So if you are dealing with transactions, like, these checkout transactions, then you possibly need the whole row, right? You want to say update something about the customer, let's say, so you want to pull the customer ID, customer name, the date and everything. So this makes sense then. But if you're doing some analytics and you only want to pull values from a column, then this is a better model. Right?
So suppose I have a query where I'm saying the mean or average salary per employee ID. I want to get that information. Then I'll be storing the employee ID with salary in that column. So that will be my tuple.
Right. So if you want to like pull, let's say 2 columns, right? Give employee ID and salary, right? So depending on there are a couple of things there.
One question is, sorry, what is the meaning of average salary per employee ID? If it's average, then it's average, right? It's not related to employee ID.
No, I think I'm answering the other. I don't know. First of all, let me clarify the question.
It's like suppose it doesn't come with salary, but some other column is there where we want to see how many we are aggregating based on the employee ID, that particular column.
So I think what you're saying is, let's say I have, for example, in one department, let's take that example, right? In one department, there can be multiple employees, right?
Right.
I want to say, okay, per department, how many employees are there?
Right. Those kind of query I want
like a grouping operation, right? The answer, the way I look at this is, you have to first look at your table. Let's say if you have 10, so you're definitely doing an aggregation there. But the question is also, how many columns are there in your original table? If you have 10 columns, right? And you're only interested in these 2 columns, right? Doing some operations over 2, then it makes sense to store them in column oriented, right? Because then you're only going to fetch kind of those two blocks and do some processing over them. But if you only have, let's say in a table, 3 columns and you're doing processing over 2, right? Then it may be beneficial to just keep it as row-oriented storage. So it really depends on what your original table looks like and how you would store your data.
So yeah, that makes sense. But I still have one more question. So what about the indexing? We have the primary index and the secondary index, and when we do operation on them, it's always faster.
Right. In column-oriented stores also, like in the SQL Server that we work with, when you store your data in column store, you can also, there are additional indexes that you can build on each of them. Like there are clustered column store indexes. I can share that. So that will help me, build an index here, and that can help me expedite, data within the columns.
Okay.
Yeah, maybe let me share some, links if you're interested in that direction. But high level, I mean, if you really go deep here, there are a lot of interesting questions that come up, right? This was just to illustrate a use case for column oriented, right? If you just want to pick one column amongst several, that's the benefit and the compression point. But if you really start using column oriented databases, you have to look at a lot of other things, right? Your original schema and how are you going to relate all these rows. Now you can also question that my columns are, how will I know that this value 1 is related to this, right? That can be another question. They are in different pages, they are not together. So yeah, I can share some links on that.
Yeah, that will be good. I can read them. Thank you, Diti. Yeah.
Sure. Okay, I think we are literally hitting 9 o'clock. But I believe we have kind of covered the summary here. If there are any other questions or discussions that you want to have, feel free to post on Discord. And I would encourage, I won't be able to attend the next session, ironically, but I will watch the recording. So I would encourage everyone to attend the session, because we might skip that in our book club.
So DP, are you sharing these slides?
I can share it if it's helpful. I wasn't sure. I
think it will be helpful because you put together everything in one place, so that will be helpful. Thank you.
Okay, sure.
Yes, please share that. That's good one.
Yeah. Okay, sounds good.
So these concepts also works in NoSQL databases?
Sorry?
These concepts are also applicable for the
NoSQL like
database.
column oriented. I think it's not exactly same, but Cassandra, if you refer column family stores, you will find some commonalities there. Yes.
Okay.
So
actually, this is
a very general concept, I think, it's I'm sure it's kind of even leveraged in NoSQL. I haven't worked on them, but yeah.
Okay. Actually, this is my first session, so I need to catch all the things.
Okay, yeah.
Yes, so please.
Feel free to message any of us on Discord, and we can talk more if you have any questions about this. But yeah, unfortunately, I would have to really make a hard stop here. It's like 9 o'clock. So please feel free to reach out, on any other things.
Okay, and please share the link of that book here.
Sorry?
Please share the link of the particular book.
Oh, so that is something I ordered. Like I have a hard copy, but I can share the link that I was using here, the GitHub one.
Okay.
Yeah.
Okay.
Okay.
Thank you, Deepti.
Thanks everyone.
Thank you.
Let me stop the recording.
Thanks everyone.